Hello Math 45 students, this is your instructor Cindy Enrique, and we are going to continue with chapter 6 on page 20. So now in section 6.6 we have exponential and logarithmic equations. So for the equations, we have an equal sign, so what we're trying to do is to solve them. So here, what this is saying, the one-to-one property, is that if we have the same bases and they're equal to each other, then that means that the exponents are going to be equal to each other. So notice here in the first example down below, we have the base. The base is 2. So it's the same base. Because it's the same base, we can use the one-to-one property and say that the exponents are going to be equal to each other. So I have x minus 1 is equal to 2x minus 4. So I'm going to go ahead and subtract x from both sides. So I'm going to get a negative 1 is equal to x minus 4. So I'm going to go ahead and add 5 to both sides. Oh, sorry, not 5. What number is that? That number is 4. So I'm going to add 4 to both sides. There we go. Got to slow my roll. So I have negative 1 plus 4. I'm going to get that 3 is equal to x as my final answer. Now for part B, notice how the 8 and the 16 don't seem to have the same base, but you can actually rewrite it, okay? So rewrite to have same base. So if we rewrite it to have the same base, let's think about how 8 breaks down. I know that 8 is equal to 2 times 2 times 2. That tells me that 8 is equal to 2 to the third power. And so if I have 16, that's really equal to 2 times 2 times 2 times 2. So that's 2 times 2 is 4. So 4 times 4 is 16. So I'm going to have that 16 is equal to 2 to the fourth power. So I'm going to rewrite this. So here I have this 8 to the x plus 2 is equal to my 16x plus 1. But we already know that we can rewrite that 8. That 8 is really 2 to the third power. And I have that x plus 2. And that 16 was rewritten as well. That 16 is really 2 to the fourth power, and it's raised to the x plus 1. So now what I can do, using my rules of exponents, I'm going to distribute my exponents. So I'm going to have 2 to the 3x plus 6 equal to 2 to the 4x plus 4. Now the bases are the same. Now I can use that one-to-one property. So I'm going to have my 3x plus 6 equal to my 4x plus 4. So I'm going to go ahead and subtract 3x from both sides. And I'm going to subtract 4 from both sides as well. So what that gives me is, well, the 3x's cancel and the 4's cancel over here. So 6 minus 4 is 2, and 4x minus 3x is just my x. Okay, so my answer is going to be that x is equal to 2. So hopefully that makes sense. So you always try to rewrite to have the same base if possible. Now for part C, hopefully you remember that whenever I have the square root of x, that square root is really the exponent of my 1/2, okay? So hint or remember. So I can rewrite this. So I really have 2 to the 5x is equal to 2. And since it's the square root, that square root is really going to be to the 1/2. So I definitely have the same bases. So 5x is equal to my 1/2. Now, to get the x by itself, since I have a fraction on the opposite side, I'm going to multiply by the reciprocal. So that's going to be a 1 over 5. So then I have x, and numerator times numerator is 1. Denominator times denominator is 10. So my answer is going to be 1 over 10. Here for part D, there is no way to rewrite having same base. It's not that there isn't a solution, it's just that right now we need something stronger. So we need a stronger property or rule. So right now, this part D, I'm going to put it on hold because we can't do this with what we know right now. Instead, I'm going to jump to this example. So here, I definitely have different bases. So I have 5x plus 2 equal to 4 to the x. So this is one where we are going to learn how to solve without having the same base. So what we do is we apply the log to both sides of the equation. So apply the log to both sides of the equation. We literally just write log in front of both of them. So log, and I have my 5x plus 2 is equal to log, and then I'm going to have my 4 to the x power. Okay. Now I'm going to be using my rules of log to solve for it. So remember, if there isn't a log base, it defaults to be a log base 10. Okay. So we are going to use the rules of logarithms. So here, one of my rules is the power rule. So I'm going to take this power and I'm going to move it out to the front. Take this power and move it out to the front. So I can have x plus 2 times, all of that is being times by my log of 5. So don't forget to distribute here. So now I'm going to have my x log of 5. Because it's addition, I'm going to have addition. And I have my 2 being multiplied by my log of 5. And it's equal to my log of 4. Okay, so now from here, I want to isolate the x variable. Oops, I forgot something here. I wrote this x where it's going to go out in front, so I have to make sure that it's out in front, okay? I even drew my little arrow here, so make sure that you follow the arrow. So now I have log on both sides. Actually I have logs on both sides, and I have x's on one side. So what I really want to do is get the x isolated on one side. So get x isolated. So I'm going to subtract x log 5 from both sides. So that way I can get the x isolated. So it's going to cancel over on the left-hand side. So I'm going to be left with a 2 log 5 is equal to x log 4 minus x log of 5. So what's happening here is now that I have an x here and an x here, I can actually factor out that x. So when I factor out that x, everything else is going to be in brackets. So I'm going to have my log of 4 minus my log of 5. And don't forget that whenever I have subtraction, that rules of log is going to turn it into division. So I'm going to have my rules of division. So don't forget, now I'm going to have log, and now I'm going to have my numerator and my denominator. So my numerator is the first thing that came, and the denominator is going to be that second log. So now I have log of 4/5. So I'm just going to rewrite that a little bit nicer over here. So I have 2 log 5 is equal to x log of 4/5. So since my goal is to get the x by itself, I'm going to divide out that log of 4/5 since it's just being multiplied. So now I'm going to have 2 log 5 over log of 4/5 is equal to my x. And this would be my exact answer. And of course, I can plug that into my calculator to get the decimal approximation. So now I'm going to be using my calculator. I'm going to punch that in. And usually we round to 4 decimal places. So x is going to be equal to a negative 14.4251 for my decimal approximation. Okay. So hopefully that makes sense. And we are going to move on to part B. So for part B, remember, I need to solve. E is just a number. Do you guys remember that we have pi, which was, let me go ahead and plug that into my calculator. Pi was about 3.14159. It keeps going forever and ever and ever. And we have E, which was very, very similar. The value of E was that 2.71828, and it keeps going on and on forever. So just remember that E is just a number. It is not a variable. It is an actual number, just like pi is a number. It's irrational. It's never ending, never repeating. So your goal, the only variable that you have is t. So, okay, so I'm going to have my 100 is equal to 20 times e to the 2t. Now, since that 20 is being multiplied, then I know the opposite of multiplication is division. So I can go ahead and divide that out. So I'm going to have 100 divided by 20, which is 5, is equal to my e to the 2t. Now, another thing that you should know, or hopefully remember, is that we had that logs, oops, let's try that again. We had that our logs, what is happening? Logs and exponential functions are inverses. The other thing that we know is that e and natural log are inverses. So since this is an e, I'm going to use ln to cancel it out. So I'm going to write the ln of 5 is equal to the ln of e to the 2t. Now, since I have ln in front of the e, it cancels out. So I'm left with the ln of 5 is equal to 2t. And since my goal is to get the t by itself, then I'm going to divide out the 2. So I can get that ln of 5 divided by 2 is equal to my t. And that is going to be my exact answer. And of course, I can always get the decimal approximation. And so for my decimal approximation, I'm going to get that t, and you usually round to 4 decimal places, is 0.8047. And I just plugged that into my calculator. Okay, so let's try doing the exact same thing with our example C. So here, what I have is E. So I'm like, okay, well, remember, E is a number. And eventually, I'm going to be using ln to isolate the variable. So the variable that I want to get by itself is x. So let's see what I can do. Let's make it a little bit nicer. I'm going to subtract 5 from both sides. So that way I can have 4 times e to the 2x is equal to 12 minus 5 is 7. Now, since that 4 is being multiplied, then the opposite of multiplication is division. So I can go ahead and divide that out. So now I have e to the 2x is equal to 7 divided by 4. Now, since I have this, that e, the opposite is going to be the ln. So ln of e to the 2x is equal to my ln of my 7/4. So don't forget, whenever I have ln and e together, it cancels out. So I'm left with 2x is equal to my ln of 7/4. So I'm just going to go ahead and rewrite it so I have more rooms. 2x is equal to ln of 7 divided by 4. Now, to get the x by itself, I'm going to go ahead and divide by 2. So then I get x by itself, and I have a fraction. The ln of 7 divided by 4 divided by 2 is equal to x. And that is going to be my exact answer. And if I want the decimal approximation, I just plug that into my calculator, and I'm going to round to the 4 decimal places so that x is equal to a 0.2798. Okay. Now, let's go ahead and move on to our natural log examples. So it says, using the definition of a log to solve logarithmic equations. So here, whenever I have a single log by itself, the order to solve for it is to rewrite it as an exponential. So log that is single and isolated will be solved by rewriting as an exponential function. Okay. That is what we're doing. A log that is single and isolated will be solved by rewriting as an exponential function. So here it says 2 ln of x plus 3 is equal to 7. So I'm going to go ahead and isolate this by subtracting 3 on both sides. So now I have my 2 ln of x, and 7 minus 3 is going to give me 4. Now that 2 is out in front, so I'm going to go ahead and divide it since it's being multiplied. So now I'm going to have the ln of x is equal to 4/2. But then 4 divided by 2 is just 2. So now what I'm going to do is I know how to cancel out my natural log. I know to cancel out natural log is by writing e. So I'm going to say that this is e to the ln of x is equal to my e of 2. So now the ln and the e cancel, so you're left with x is equal to my e squared. So my exact answer is x is equal to e squared. And of course, I can give the decimal approximation. So I just plug it into my calculator and I round to 4 decimal places. So x is equal to 7.3891 as my final answer. Now, I'm going to go on to my next example. I have 2 natural log of 6x is equal to 7. So I don't have any addition or subtraction. I always try to do that first. So since it's being multiplied by 2, to get rid of it is to divide by 2. So now I have the ln of 6x is equal to 7/2. So the ln is there. So remember, the inverse function is e. So e to the ln of 6x is equal to e of 7/2. Whenever I have ln and e together, they cancel out. So now I have 6x is equal to my e to the 7/2. To get the x by itself, I'm going to divide by 6, since that is the opposite of multiplication, so that x is equal to, and it's going to be a fraction, I have my e to the 7/2 divided by 6. And that is going to be my exact answer. And of course, I also have my decimal approximation. I plug that in and round to 4 decimal places, so that x is approximately 5.5192. I'm going to go ahead and write that a little bit nicer. I wrote that too fast. 5.5192. There. Sometimes my writing does get a little bit messy, so I do apologize for that. Okay. So here are some more examples on page 23. We are still solving for the natural log for that first example. So I have the 2 out in front. It's being multiplied. So I'm going to go ahead and divide it out. So I'm going to get the ln of my 3x plus 1 is equal to 10 divided by 2. But I know that 10 divided by 2 is just really my 5. And since I have ln, I'm going to have my e that I'm going to write it as. And whenever I have ln and e together, it cancels out. So now I have 3x plus 1 is equal to e to the 5th power. So I'm going to go ahead and subtract 1 from both sides. So I can have that 3x is equal to e to the 5 minus 1. And then from here, divide by 3, divide by 3, and it's divide everything by 3. So I can get that x is equal to the fraction e to the 5th minus 1 divided by 3. Okay. And the decimal approximation here would be that x was equal to a 49.1377 for the decimal approximation. For the next example, it's slightly different because now we're jumping into logs again. So the logs, what we're going to have to do is write it as a single logarithm and then rewrite it as an exponential. So here I have addition. The addition of logs tells you to multiply the insides. So now I'm going to have my log base 2. I'm going to be multiplying the insides. So here I have 2, and it's being multiplied by my 3x minus 5. And all of this is equal to 3. So now I'm going to rewrite this. I have log base 2, and it's still equal to 3, but now the inside I'm going to have to distribute. So I'm going to have a 6x minus 10. Now I'm going to rewrite it as an exponential. So here my base is 2 and my exponent is 3. So I'm going to rewrite it as 2 to the third power is equal to my 6x minus 10. So 8 is equal to 6x minus 10. So I'm going to add 10 to both sides. So 18 is equal to 6x. So 18 divided by 6 is equal to x. And of course, if I were to simplify that, I will have that 3 is equal to x as my final answer. Again, for the next example, I have logs and I have addition. So that's going to turn it into multiplication. So I'm going to have my log, and I'm going to have this all multiplied, and it's going to equal to 1. So here I have x, and I'm multiplying it by the x plus 3. So I'm going to have log. I'm going to go ahead and distribute. So I'm going to have an x squared plus a 3x all equal to 1. Remember, if there isn't a base there, it defaults to 10. So base defaults to 10. So this is really log base 10 of x squared plus 3x equal to 1. So if I were to rewrite it as an exponent, then I have my base and I have my exponent. So for my base, that's 10. My exponent is 1, and it's equal to that x squared plus my 3x. Of course, I want to set it equal to 0, so I'm going to subtract 10 from both sides. So that way I can have 0 is equal to x squared plus 3x minus 10. From here, I'm going to factor since it's an exponent of 2. So 5 times 2 is equal to 10, and it would be a positive 5 and a minus 2. So x plus 5 is equal to 0. So x is equal to a negative 5. X minus 2 is equal to 0. So x is equal to a positive 2. And we know that x minus 5 can't be the answer because the argument is that the inside of the log must be greater than 0. So if we have x is equal to 2, that is going to be the only possible solution that we have. So x is equal to 2 is the only answer that we have. Okay, so here's our next example. Now for this one, we actually have something slightly different. We have subtraction. Because it's subtraction, then we should know that we're going to have a fraction. So I have log base 4. I'm going to have a fraction that's equal to 2. So in that numerator, I have an x plus 2 because that came first. The fraction that came second goes in the bottom, so that's my x minus my 4. So now I'm going to rewrite this as an exponential. So my base is 4, my exponent is 2, and it's equal to my x plus 2 over my x minus my 4. So 4 squared is going to give me 16. So now I have that 16 is equal to x plus 2, x minus 4. And there's a lot of different ways that you can solve for this. For me, I'm going to go ahead and do a cross multiplication. So I can have that 16 times x minus 4. It's going to be equal to the opposite, the cross multiplication of that. So it'd be 1 times my x plus 2. So I'm going to have a 16x minus, and 16 times 4 is a 64. And on the opposite side, I have my x plus 2. So I'm going to go ahead and subtract x from both sides, and I am going to add 64 to both sides. So 16x minus x is going to give me a 15x. And 64 plus 2 is going to give me 66. So now from here, divide by 15 on both sides. So I can get that x is equal to 66 divided by 15. And of course, you can also, I believe there's a decimal approximation. So x is going to equal to a 4.4. Okay, and that's going to be my final answer. Actually, you can simplify further. You can divide by 3 on both sides. So 66 divided by 3 is 22, and 15 divided by 3 is 5. Always simplify if possible. Okay. All right. Now it says using the one-to-one property of logs to solve logarithmic equations. So now if we have a single log is equal to a single log, then the inside of those logs must be equal to each other. So let's try that out for the first example down below. It says natural log of x squared is equal to the natural log of x plus 2. So I have a single log equal to a single log. So that means that the insides are going to be equal to each other. So x squared is equal to that 2x plus 3. So x squared is equal to that 2x plus 3, since we are using the one-to-one property of logs. So I'm going to set this equal to 0. So I'm going to have my x squared minus 2x minus 3 is equal to 0. So since it has an exponent of 2, I'm going to go ahead and factor. I know that 3 is prime, so 3 times 1 is 3. And a minus 3 and a positive 1 gives you a negative 2x. So I'm going to have x minus 3 is equal to 0. So x is equal to positive 3. X plus 1 is equal to 0. So x is equal to a negative 1. Don't forget that the inside of the log or natural log must be greater than 0. So when I plug 3 back in, 3 squared, that's 9, that's fine. So 2 times 3 is 6, plus 3, that's positive. So the inside of the log still remains positive. When I plug in that negative 1, x squared, negative 1 squared is 1, so that's fine. 2x plus 3, 2 times negative 1 plus 3, that's positive. So that's fine as well. Okay, so don't forget, plug back into original to make sure insides are positive. Okay. Now for the next example, I have log base 2 equal to a log base 2. So that also tells me, since I can use the one-to-one property, that the insides are going to be equal to each other. So I'm going to have that 2x plus 1 is equal to my 3x minus 5. So I'm going to go ahead and subtract 2x from both sides. So I can get that 1 is equal to an x minus 5. So I can add 5 to both sides. So I can get that 6 is equal to my x. And that's it. That's going to be my final answer. Now for the next example, how many natural logs do I have? I have 3. So that means I need to combine it so it's isolated. So here, I'm going to condense that ln on both sides. So I'm going to have this as addition, so that tells me I'm going to multiply. So ln, and it's equal to my ln of 12x. So I want to condense this. So I'm going to have my x, that's here, and it's going to get multiplied by something else. It's going to get multiplied by the x plus 5. So I'm using my rules to go ahead and condense that equation. So now I have natural log, wrong color. I have my ln, and since I want to distribute, I'm going to have an x squared plus a 5x, and it's still equal to my natural log of my 12x. Now I have a single natural log equal to a single natural log, so now the insides can be equal to each other. So x squared plus 5x is equal to my 12x. So then from here, what I can do is I'm going to go ahead and subtract that 12x to the opposite side. So x squared plus 5x minus 12x is equal to 0. So then I have 5x minus 12x, which is a negative 7x, is equal to 0. So if I factor this, I'm going to factor out an x. So x minus 7 is equal to 0. So I have x is equal to 0, and x minus 7 is equal to 0. So x is equal to a positive 7. The x is equal to 0, we'll try it. If you plug in natural log of 0 onto your calculator, now I'll do it as well. ln of 0, I get error. It has to be strictly greater than 0. So the x is equal to 0, we throw that out. Remember, we always want to check our solutions in the actual original equation. So if I have x is equal to 7, that actually works out. So my final answer is just going to be that x is equal to 7. Okay, and that is the end of section 6.6. If you have any questions, please email me or contact the Math Success Center